So, good day, and we're here again with another lecture for Engineering Calculus 2. I am still your lecturer for this subject, and our topic would be about the definite integral and area of a plane region. So, from previous lectures, we discussed a lot about indefinite integral and some techniques how to find the antiderivative with the constant of integration. So this time we will be looking at the definite integral as well as area. So learning outcomes for this is to evaluate the definite integral using the same techniques that we employed in antidifferentiation of the indefinite integral. So you can read through, and we our one of our outcomes also is to analyze a quantity A or area as a summation of the changes in area over an interval AB, and also to approximate this area by a product or a function fx dx, and conclude that A is the definite integral, the integral from A to B of fx dx. So this part would be more on explanation and derivation and proving. Okay, so for our lecture outline today, the first part will be about the measure of an area bounded by a curve as a limit. We will also discuss this area as a limit of a Riemann sum. So later on we will define what is the Riemann sum, and eventually this will lead us to the definition of our definite integral. We'll also present some theorems for the definite integral as well as some examples. So now let's begin. Now let's talk about area. So we have here, as you can see, a curve denoted by y is equal to f of x, and we have two lines here. You can see A and B, lines A and B, which are within the bounds of our curve, or we can say that are continuous in y is equal to f of x, whatever the equation of that function or that curve would be. And we can see we have here the x and y axis, and we have here a region bounded by lines A, B, the positive x axis, and the curve, or basically it is a area under our curve. So let's call that area A. So now we wish to know how we can find the area or the measure of the area of A, given these conditions. We have a function, we have the bounds. First of all, we are talking about measure of the area. Okay, so this would be in square units, whatever unit you want to think of. If we say measurement, that should give us the measure plus the units. Okay, be it centimeter squared, meter squared, or whatever length squared unit you can think of. Okay, so just to make it clear, the measure of the area doesn't necessarily have the units, but when you said measurement, then you need the units. Okay, so now how then could we define this area A or find this area A? So what we are going to do is to that the same curve, we will inscribe polygons, particularly these rectangles, under that particular curve. So we all know that the let me write here somewhere that the area of a rectangle is just equal to the length times width. So in this case, the width would be on the x-axis and the length would be on the y-axis. Okay, so I think you already have a hint now that what we are going to do is just to take the areas of each of these rectangles here, inscribe in our um, in the area under the curve bounded by a and b, the interval a and b, and add up their areas. So that would give us not exactly the area, because you can see we have here some, you can see the spaces, right, which are not accounted for. So we can approximate the area under this curve by taking the summation of the areas of these rectangles. So then we should define we should know what is the width and the length of this rectangles. Okay, so for simplicity, let's take the width of each of these rectangles as equal. Okay, so it might not look equal to you, but let's assume that all of this width are equal. So each of these measurements here, let's call it change in x or delta x. Okay, so the width of the each of the rectangles would be equal to delta x. So they are equal from each other. So it means that if we subtract if we subtract a from b and divide it into delta x measurements, we will have the number of these rectangles. Or let's call the number of these rectangles, or the number of subintervals. We have here the interval a and b, and we divide it into smaller intervals, subintervals. So let's call that n. So we have n subintervals. And this n is determined by n would just be equal to the measurement of b minus a. That would be here from here. Oh, sorry. I'm not. Okay. Divided by delta x. Or we can rearrange this equation and we can find the value of each delta x by this equation. So b minus a divided by whatever number of subintervals you wish, whatever n you wish. That would be the measurement of delta x. So that is for our width. So for our length, okay, so let's define first the points here, the endpoints of our interval as, So I will write x sub o, that would be equal to the first endpoint, which is a, and the rightmost endpoint b. Let's call that x sub n. Okay, so in between them here you have, let me write here, x sub 1, you have x sub 2, and from here b, this one would be x n minus 1. Okay, until x n minus 1 until you reach x sub o, which is a. Okay, so we have x1, x2, x3, and so on. Okay, now let's go to, for the length, we have what we call, for this subintervals, we have what we call the extreme value theorem. So it says that for each of these subintervals, there is an absolute minimum value for our for the function y. Okay, so if you, let's take the interval bounded by x sub 0 to x sub 1. So from this function y, the minimum value is, you can see it here, right? So this is the minimum value for this subinterval. For the next subinterval, this is the minimum value of the, we are looking for the values of y. Okay, so here you have this minimum value, for the fourth one you have this, and so on, right? Okay, so the extreme value theorem says that for each of the subintervals, there is an absolute minimum value, and let's call that minimum value as c. Let's call that minimum value c sub I, or since we are a function, call it f of ci. Okay, so for the first one, this would be c sub 1, the next one that would be c sub 2, and so on until we reach c sub n. Alright, so now if we can define f as a function of c sub I, and we already decided the number of intervals, thus we will have a value for delta x, then for the rectangle, the equation would be f c of, let's take the first rectangle, that would be c1 multiplied by delta x. For the second rectangle, that would be f of c sub 2 delta x, and you can see the pattern here, f sub c3 delta x, until we reach f c sub n for the number of intervals or subintervals that we have. So in sigma notation or summations, let's take the summation of the areas of all these rectangles as s of n, s of n. So in sigma notation, that would be the summation, we put n here, I is 1, the summation of f of ci, c1 up to cn, multiplied by delta x. So s of n which is the summation of the areas of the rectangles here that we subdivide our region, could approximate our area A. So A, as we mentioned earlier, is the area bounded by A to B and the x-axis. And as you can see here, S sub n, which is the summation of all the areas of these rectangles, will always be less than or equal to A, right? Because of this, you can see this shaded regions here, which are not yet accounted for. So S sub n would then be less than or equal to our area A here. Okay, so this is area A, the whole thing. So what we need here is for S of n, or the summation of the areas of each of all the rectangles, to be near A, which is the area under the curve. So what if we increase the number of our subintervals? Let's say we double it. Okay, so for now, we double the number of our subintervals. And what does it look like? So it looks like the area of the here, the area of the shaded region here decreased, right? So it means that if we compute for S sub n here, that would be different from our first figure, where the number of subintervals is half of this, right? So as you can see, as we increase the number of subintervals, that is, we increase the number of rectangles, our S of n is having different value and is becoming closer and closer to, it is still less than or equal to our area under curve A, but as we increase the number of intervals, it approximates A closer and closer. Alright, so we can say that as n approaches or increases without bound, that is, approaches infinity, the value of S of n becomes closer and closer to the area that we wish to approximate. So we can write, we are looking for this limit where n is getting increases with no bound up to a limit wherein S of n would be equal to A. So this is now our definition of the area. So let me write it here. The definition of our area here, which is bounded by the curve, is the limit. So A, this is the area that we wish to find. This is the limit as the number of subintervals n approaches infinity. So the summation upper bound is n, the first one is 1. So this is still the equation earlier, which is f of ci multiplied by delta x. So this is the limit that we are looking for. So the definition of our area is this. So it is the limit as n, or the number of subintervals, or if you want to put it simply, the number of rectangles here approaches or increases with to no bound, or approaches infinity, and we take all the function of ci, whatever number of intervals we have, multiplied by, remember, we still have the same width for each rectangles. So I will just leave it to your imagination if you want to double the number of these rectangles, how much this shaded area here will decrease until it's completely gone and A is almost equal to S sub n, which is the summation of the areas of this rectangles. So that is the definition of our area bounded by this curve. So now let's proceed to another limiting process, which is somewhat similar to the first limiting process that we did to define the area bounded by a curve. And this time we have this curve here bounded by both the y and x axis, and we wish to know what is this, the area bounded by this curve here. So once again, what we're gonna do is we will divide this area into subintervals which are composed of rectangles. Okay, so you can see this lines, blue lines, comprising our rectangles. So now if you can notice, our rectangles here are protruding from the bounds of the curve, right? Only one of them, this one here, didn't protrude from our curve. Okay, so again, we divided our area into an n number of subintervals, but this time the widths of these subintervals would not necessarily be equal. Okay, so let's write our bounds here. So let's start with x sub o, the next one would be x sub 1, next one is x sub 2, and eventually the endpoint would be x sub n. Okay, so the distance between x sub 1 and x sub o, let's write that as x sub 1 minus x sub o, would be equal to the width, which is, we will call delta 1 x. So for the second rectangle here, that would be x sub 2 minus x sub 1, that would be delta 2 x, and so on until we reach the last subinterval, or we can write it down as x of I minus x I minus 1 would be equal to delta I x. So our width here would be delta I x. So the set of these distances here that are not equidistant to each other for this area that we wish to calculate would be called the partition. So such set of delta 1x, delta 2x, and so on until delta nx, the set of those measurements is called the partition. So the longest width, or the longest xi minus xi minus 1 is called the norm and is denoted by this. So when you see this, this is the norm. It describes the longest subinterval. Okay, so that is all about the width. So for the length, as you can see here, as the number of subintervals is decided by us, so we can pick a point, choose a point here which is arbitrary, and let's call it w sub I, or for the first rectangle that would be w1, the next one would be w2. So if you can recall, this would be the same as c sub I from our previous limiting process. So for the length, our length here would be a of function of w sub I. Okay, so for the first rectangle, that would be f of w sub 1. The next one would be f of w sub 2, and until we reach w sub n. So the same as before, we will compute the area for each rectangle and we will do the summation of that. So for the sigma notation, that would be the summation from I is equal to 1 up to n of the length f a function of wi. So it's still the area of a rectangle, that's length times width. So the length times the width, which is delta I x. So this type of sum is called the Riemann sum. It's named after a mathematician named George Friedrich Bernhard Riemann. So this is our Riemann sum. And now let's recall the definition of our norm as the longest delta I x, so, or the interval with the longest difference of xi minus xi minus 1. Okay, so that is our norm. And what we want to know is what should be the area bounded by this curve. But as you can see, we have protrusions here. So if we say that our Riemann sum is maybe more than our area, minus a, so we want the difference to be as small as possible, or as much as possible equal to 0, right, in order to approximate the area of bounded by this curve. So we want our Riemann sum, the difference of our Riemann sum and our actual area, to be as small as possible or to become zero. And how can we do that? We can do that by letting our norm to be as small as possible, or in other words, letting our norm approach as small as possible or as it approaches zero. So imagine if let's say x1 minus xo is our norm, and this is our the rectangle produced, and we have this much protrusion here. Imagine if we take that in half, or even divided by 4, divided by 8, or as small as possible. So we can make all these protrusions here disappear, thus making our approximation um, very much bounded by our curve, and making it as close to a as possible, and the difference to be zero. So now we define our area here. Let me write that our area must be equal to the limit of the Riemann sum, the limit of this, our Riemann sum here, as our norm approaches zero. So let me just rewrite everything here. We have n summation I equals 1. So again, this is the limit of our Riemann sum as the norm approaches 0. So that is our new kind of limiting process to define the area bounded by our curve. Okay, so the area under the curve will just be the limit of our Riemann sum as the norm approaches 0. So if we let our endpoints here xo equals a and xn equals b as before, and we have a sufficiently small norm across the interval, we can see that our function f is integrable in the in the interval ab. Okay, so our function is integrable, therefore we can integrate it from a to b. Now we have defined the limit of the Riemann sum, so we can define the definite integral. So we have this equation: the integral from a to b of fx dx is equal to the limit of, this is the basically our Riemann sum equation as the norm approaches 0. So the theorem is, if the function is continuous on the closed interval ab, which we have shown in our derivation earlier, then it is integrable on the interval a to b. If it's integrable, then we can write it, the function from a to b, the integral of that is just equal to the Riemann sum as the norm approaches 0, or as the norm becomes very small. to approach 0. So then, this is the definition of our definite integral. Okay, so here are some theorems for operating on the definite integral. So we have this familiar equation, and on the other side, it would just be equal to the negative value if the bounds are reversed. So if we started from B to A, that would be a negative value. Also, we can we can see here that if you integrate from A to the same bound A, that would just be equal to 0. It means you didn't really cover any area. Here we have a constant, so the same as for the theorems presented from our earliest lessons, you can just take the constant from outside the integral sign. So we also have this theorem when you have two functions, fx plus gx dx, it will just be equal to integrating fx dx from a to b plus integrating g of x from a to b. And if you have three bounds in the function a, b, and c, regardless of their succession, even if c is less than a is less than b, or whatever is the succession of these bounds. So if you integrate from a to b, that would just be equal to the integration from a to c fx dx plus the integration from c to b of fx dx. So those are some of the useful theorems when operating on definite integrals. Now let's have an example. So suppose we need to find the definite integral from 0 to 2 of this equation, 4 minus x squared dx. Okay, so our lower bound would be 0 and our upper bound would be 2. So how can we find the definite or the exact value for this function? So notice that this function is, you can write it like y is equal to the square root of 4 minus x squared. And recall that the equation of a circle is x squared plus y squared is equal to r squared. So this gives us the equation of a circle. If we square both sides here, you get y squared equals 4 minus x squared. Rearranging, that would be x squared plus y squared equals 4, or that's 2 squared. So it means that our equation here is an equation of a circle with the radius 2. So r equals 2. But as you can see from the original equation, y is equal to the square root of 4 minus x squared, it is looking for only the positive half of it. So if you take a Cartesian plane, let me write here. We're only looking for a semicircle. That is the upper part of it. So we're looking at a semicircle with radius equals 2. Okay. So if this is 0 and this is 1 and this is 2, then we are looking for the area of this region only, which is a quarter of a circle. So we all know that the area of a circle is equal to pi r squared. And for this problem, we are looking for a quarter circle. So this is for a full circle, so we just divide it by 4 for this one. And substituting the radius 2 here, we have pi 2 squared, that would be 4. And we just need the quarter circle, so we need to divide by 4. So our answer for this problem is pi, or 3.1416 square units. So let's try another example. Let's have the integral from 0 to 3 of x, the square root of 1 plus x dx. So for this one, we'll be using u substitution. So we let u be equal to the square root of 1 plus x. If we square u, therefore u squared is equal to square root of 1 plus x squared is 1 plus x. Therefore we can find the value for x. We can write x equals u squared minus 1. And if we take the derivative of x, that would be dx. That would be equal to 2u. This would be 0, so 2u du. Okay, so now substituting to our equation, let's write it in a different color here. Okay, so the integral from 0 to 3 of x, this is x is u squared minus 1 multiplied by u. This is 1 plus square root of 1 plus x is u, so multiplied by u, and dx is 2u du. Okay, so combining all of this, so we will get our equation is definite integral from 0 to 3 of this would be u squared, u cubed, and u to the fourth. So that would be, we can take out this constant 2, so that would be u to the fourth minus, that would be 1 times u times another u, since we already took out 2, so that's u to the fourth u squared du. So that looks like um, very, compared to the first one, this one is easier to integrate. So let's find the antiderivative of u to the fourth and u squared. We can separate them if you can recall from our past lessons. So let me write it here. So I have here 2 multiplied by, that would be u to the fifth power all over 5 minus u to the third power all over 3 plus constant of integration. Look here, we're just still looking for the indefinite integral for this. The c here will disappear when we apply the bounds, the lower limit and the upper limit here. Okay, so in short, our integral would be, sorry, our equation, so the equation would be 2 u to the fifth all over 5 minus 2 u cubed all over 3 plus 2 times c, that would just be constant of integration. So now what we need to do is just to substitute the value of u here, which is equal to the square root of 1 plus x. We can directly substitute our bounds here, since these are in terms of x and we substituted u in here. So let's plug in this would be 1 plus x to the 1/2. Okay, so we'll plug in here to this u, so we get 2/5 of 1 plus x, that would be to the 5/2 minus 2/3 1 plus x, that would be to the 3/2 plus c. This is our equation, and now the thing left to do is to plug in our lower and upper bound. So first we will plug our okay, let's just continue with the equation here. So the first one would be okay, we can write it in this way without writing the c. We can write it from here from 0 to 3. So what we're going to do is, first we will substitute 3 for x. We will compute the result, and then we will subtract the expressions when we substitute 0 in here. Okay, so it's basically upper bound minus lower bound. So first, for 3, this would be, let me use a bracket here. So 2/5 of 1 plus 3, that would be 4 to the 5th power, and take the square root of that. Of course, minus 2/3, still 4 to the 3rd power, and square root of that. That would be our upper bound, and minus, again, we will just take this equation and substitute 0, so that would be 2/5. That would be 1 plus 0, so you still have a value. So it's not always that the second term or the lower bound will be 0, so be careful. Okay, so they will, even if the lower bound is 0, the second term will still have a value. Okay, so if you plug all of that in your calculator, you will arrive in the answer. So I will just take the simplifications here. So this would be 64 over 5 minus 16 over 3, and minus, again, that would be 2/5, 1 raised to any power, minus, or this would be, okay, this is minus, so this is also minus 2/3. Okay, so let me write the answer here on the top corner. So combining all this would be 64 over 5 minus 16 over 3 minus 2/5 minus 2/3. So this should be in parentheses, so please don't be confused with the operations. So this is minus times minus, so that would be eventually plus later. Okay, so the answer is 116 over 15. So this is our answer for this. This is the exact value of this definite integral. So our source for this content is still our reference book, The Calculus 7 by Louis Leitholt, and you can find this lecture or lessons from pages 346 to 367. So as always, thank you for your attention.